understanding the migratory patterns of large tuna species. The Atlantic bluefin tuna is an emblematic species. It has suffered severe overfishing because of its great commercial value. Its culinary properties are highly prized around the world, particularly on the sushi and sashimi market. Built for speed and endurance, bluefins can travel up to 10,000 kilometers in a single year. Their two main spawning grounds are in the Gulf of Mexico and the Mediterranean Sea. As top predators, bluefin tuna play an important role in maintaining the ecological balance of the marine environment. The largest of all tuna species, they can reach 600 kilos in weight. Scientists are now exploring minimally invasive techniques that will provide information on its biology, habitat and migratory patterns without harming the fish in an attempt to sustainably conserve the species. By analysing the first dorsal fin spine bone of freshly caught bluefin tuna, we can learn more about this fascinating species without damaging the animal. The fish are then released back into the wild. Fin spines are part of the fish's endoskeleton. Like tree trunks, they develop distinctive layering patterns as the animal grows. If we take a cross-section, we see a seasonal banding pattern. Each annulus is formed annually and represents 1 year in the fish's life. It contains two bands, a thick one formed in the spring and summer, followed by a narrower one formed in the autumn and winter. Our analysis of these annual growth bands provides important information that helps us understand the species' migratory patterns. Fin spines contain hydroxyapatite, the mineral component commonly found in teeth, bones and fin spines. We aim to analyse the biological isotopic signature of this biomineral. Thus, to obtain the part we wish to analyse, we first embed the fin spines in a resin block and obtain a section of 0.5 mm in thickness. The sections are then digitalised and individual annuli are selected and milled. Finally, we analyse the isotopic content of the powdered material from each annulus. But what is an isotope? Isotopes are variants of a chemical element. All isotopes of a given element have the same number of protons in each atom, but a different number of neutrons. Let's briefly remind ourselves of the structure of an atom using the example of oxygen, a crucial element for this study. Like any atom, an oxygen atom has a nucleus made up of protons and neutrons, and an outer shell containing the electrons. Our work focuses on two natural stable isotopes of oxygen, oxygen-16, by far the most abundant, and oxygen-18. Both have 8 protons. But whereas oxygen-16 has 8 neutrons, oxygen-18 has 10, and is often referred to as the heavy isotope of oxygen due to its higher atomic mass. As we can see, the oxygen-18 isotope is heavier because it has 2 extra neutrons. Water molecules, which are made up of 1 atom of oxygen and 2 of hydrogen, act differently depending on which of the 2 isotopes of oxygen they contain. Thus, water molecules with oxygen-18 weigh more. As a result, water with the lighter oxygen-16 evaporates slightly more readily, while oxygen-18 needs warmer water temperatures to evaporate. Both forms are found naturally in the ocean. When the temperature rises, water molecules with oxygen-16 are the first to evaporate. But also, as water vapour condenses to form rain, oxygen-18 precipitates first because it's heavier than oxygen-16. Consequently, the O18-O16 ratio in the seawater is linked to salinity through the precipitation-evaporation balance. How does this affect our target species? Marine life is in isotopic balance with its environment. As the fish grows, the tuna's fin spines take on the characteristic isotopic signature of the surrounding water. But the final ratio in the fin spine also depends on the seawater temperature. and so in cooler waters, they retain more oxygen-18. By analysing the O18-O16 ratio in the fin spine, also known as delta O18, we can determine the characteristics of the water's origin. In this way, by analysing this ratio in each annual growth band of the tuna fin spine, we can produce retrospective isotopic profiles that enable us to chronologically reconstruct the different waters where the fish have been living. And then trace the migration pattern. By using this non-invasive approach, we can establish the age at which fish leave the spawning grounds to feed and grow, and when they set out on the great return journey to reproduce in turn. We can use this information to improve conservation of the species and ensure responsible tuna stock management, helping ensure a healthier sea.